Hello children, welcome to mathematics class. Today we are going to do chapter 10 of class 10 circles. Children, you already know that circle is a collection of points which are at a fixed distance from a fixed point. The fixed point is called the center of the circle and the fixed distance is called the radius of the circle. You must have come across various examples of circles from your daily life. Let us recapitulate a few terms related to circles. A line segment joining any two points on a circle is called a chord. Like in this figure, ED is the chord. Chord of the circle passing through center of the circle is called diameter of the circle. Clearly, diameter of a circle is twice the radius. A portion of the circle is called an arc of the circle, like arc PQ. Region of the circle bounded by two radii and an arc of the circle is called sector of the circle. Region of the circle bounded by a chord and an arc of the circle is called segment of the circle. Now let us examine which situations can arise if we have a line and a circle in the same plane. There can be only three possibilities. The line PQ and the circle have no common point. So PQ is non-intersecting line with respect to the circle. Another case is the line PQ intersects the circle at 2 points. Let the 2 points be A and B. In this case, PQ is called secant of the circle. Case 3, the line has just one point common to the circle. In this case, PQ is called tangent to the circle. The word tangent comes from Latin word tangere, which means to touch, and was introduced by Danish mathematician Thomas Finnecke in 1583. So children, we can define tangent as follows. Tangent to a circle is a line that intersects the circle at only one point. Children, have you ever observed examples of tangents to a circle from things around you? You must have seen a pulley fitted over a well used for taking out water from the well. If we consider rope on both sides as a ray, it is like a tangent to the circle representing the pulley. You must have seen wheel of a train. This wheel touches the edges of a railway track at only one point. This is also an example of a tangent represented by track to the circle represented by the wheel. Children, let us do an activity. Here I have taken a circle and I have marked a point here. I have taken this thin needle which is representing a line segment, and here it is behaving as a tangent when it is touching the circle at only one point. Now if keeping the position of this line segment here at P, I move it slightly, I see that it is cutting the circle at different points. So here, this is a line segment which is touching the circle at only one point. But when we move it, keeping this position fixed, we see that it is cutting the circle at different points. The first point being the same, that is P. So the points can be, when it is moved, the points can be P and Q1 or P and Q2 or P and Q3. That is, it is a secant in those cases. Earlier, it was touching the circle at only one point. So this line segment which touches the circle at only one point is called a tangent to the circle. Or we can say that tangent is a special case of the secants where it is touching the circle at and only one point. So children, let us do another activity. Here I have drawn a circle and I have drawn a secant which is cutting the circle at 2 points P and Q. So we can say that PQ is the corresponding chord to the secant. Now we'll draw many more secants which are parallel to this secant. So children, now I have drawn many more secants which are parallel to the given secant. You can see that the length of the corresponding chord, it is decreasing. So the point of intersection of the circle and the secant is coming closer and closer, and ultimately the point of intersection, it coincides. At the point when it coincides, this is called tangent to the circle. So you can say that a tangent to the circle is a special case of the secant when the point of intersection of the chord and the circle, it coincides. You can see that there can be only two tangents which are parallel to the given secant for the circle. Children, we have already discussed how railway track is like a tangent to the wheel of train. Similarly, ground is also a tangent to the wheel of a bicycle, isn't it? Now, don't you think ground appears to be at 90 degree with the radius of the wheel? Let us try to prove this. So children, we are going to do the theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. So here I have taken a circle and this is the tangent xy. We have to prove that this tangent is perpendicular to radius at this point, at the point of contact. Let me mark this point as point P. So what is given here? It is given that we have a circle with center O, xy is tangent to circle at point P. What do we have to prove? We have to prove that this tangent xy is perpendicular to the radius OP. We have to prove this. So let us try to prove this. What are we going to do? We are going to take any point Q on this tangent xy. So let me take a point Q. Let Q be a point on xy. Now what do you think? Q will lie outside the circle or will it lie inside the circle? Certainly it will lie outside the circle, because suppose if it lies inside the circle, that would mean that xy is cutting the circle at 2 points, which is not true because it is a tangent, it is not a secant. So clearly Q lies outside the circle. So if we join O with Q, can we say that OQ is greater than OP? Because Q is lying outside the circle, distance of Q from the center will certainly be greater than radius of the circle, because OP is radius of the circle. So OQ is greater than OP. Similarly, this will be true for all points lying on XY. Except P. So you take any point on xy other than P, its distance from the center will always be greater than OP. So we can say that OP is the shortest distance from point O to xy. So this implies OP is shortest distance of O from xy. And children, what is shortest distance of a point from a line is called? It is called perpendicular. So we can say that OP is perpendicular to xy because the shortest distance is perpendicular to the line segment. So we conclude that at any point on a circle, there can be one and only one tangent. The line containing the radius through the point of contact is also sometimes called normal to the circle at the point. So children, based on what we have studied in the theorem, let us do a very simple question. The question is, a tangent PQ at a point P of a circle of radius 5 cm meets a line through the center O at a point Q such that OQ is equal to 12 cm. So here we are given that circle and we are given that the radius is 5 cm. This is the tangent at the point P and a line through the center meets this tangent at the point Q such that OQ is equal to 12 cm. We have to find the length of PQ and we have been given 4 options. The 4 options are 12 cm, 13 cm, 8.5 cm and square root of 119. Now let us see whether with the help of theorem we can find it easily. Now we know that the theorem says that the radius is perpendicular to the tangent at the point of contact. So this angle will be equal to 90 degree because the point of contact is point P. So we will say that angle OPQ is equal to 90 degree because radius is perpendicular to tangent at the point of contact. Now if this is 90 degree, can we say that this triangle is a right angle triangle? Yes. So in right angled triangle, OPQ, which is the common property we often use in right angle triangles, that is Pythagoras property, which says that square of the hypotenuse is equal to sum of squares of the legs of the triangles. So this is by Pythagoras property or Pythagoras theorem. So let us put all the values that we know. We know the value of OQ. So 12 square is equal to OP square, that is 5 square plus PQ square. We need to find the value of PQ. 12 square is 144. 5 square is 25. So 144 minus 25 is equal to PQ square. So when you subtract, we will get 119. Let us square root both sides. We will get square root of 119 is equal to PQ. And children, we had to find the value of PQ only. So which option is correct? So D option is the correct option. Now children, let us take a supposition that we have a circle and a point. Now what can be all the possibilities of this case? It is possible that the point lies inside the circle or the point lies on the boundary of the circle or the point lies outside the circle. Can there be any other possibility? No. We have done in smaller classes that if there is a point and a circle, either it lies in the interior or the boundary or the exterior of the circle. So we have taken all these 3 cases. Now what can be the possibility? If we want a tangent which passes through point P, is it possible in this case that there is a tangent which passes through point P? Now if I try to draw any line passing through point P, you can take any number of lines. You will find that all these lines, they are cutting the circle at more than one point, that is 2 points. So clearly it is not a tangent, it is a secant. So there is no tangent which passes through point P if point P is in the interior of the circle. Now when the point P is on the boundary of the circle, I want to draw a tangent which passes through point P. Can I draw it? Let us see how many tangents are possible. So this is one tangent. Can we have some other tangent? Now if I try to draw other tangent, whatever position I may take, it is always cutting the circle at more than one point, that is, it is a secant. So how many tangents are possible at the point P? 1 and only 1. So there is only one tangent passing through point P when point P is on the boundary. What about if the point P is in the exterior? How many tangents can be drawn? Let us try. Now this is one tangent. And this is the other one. I could draw two tangents. Can I draw some more? Let me try. If I draw some other lines, I'll find that this is a line passing through point P. Clearly, when extended, it will cut the circle at more than one point. That is, it is cutting the circle at 2 points. And a line passing through the circle and cutting it at 2 points is called a secant. So clearly it is not a tangent. So I have found only two tangents. Children, you can try at home and try to find some more tangents if you can. But I am sure for a point P in the exterior of the circle, you will find only two tangents. Now the point of contact of these two tangents, let me name them as T1 and T2. Now let us try to measure PT1 and PT2, that is the segment of the tangents from the external point to the point of contact. Let me try to measure it. Here I have found it 23 centimeter and here again it is 23 centimeter. So children, I have this very good observation, that very nice observation, that the segment of the tangent from the external point to the point of contact are equal. Right? So if we have two tangents drawn from the external point and we measure the segment from the external point to the point of contact, for both the tangents they are equal. So is it true for all the tangents? Let us try with the help of a theorem. So children, let us prove our observation in the form of a theorem. The theorem, which is the general form of our observation, is the lengths of the tangents drawn from an external point to a circle are equal. That is, if we have an external point P and we have two tangents, you can see that PQ and PR are tangents. They are touching the circle at only one point. We have to prove that PQ is equal to PR. What are we given? A circle with center O and point P, which is lying outside the circle, to prove PQ is equal to PR. Now children, how can we prove this? We know that we have done through a theorem that the tangent is perpendicular to the radius at the point of contact, right? So this is the tangent, this is the radius, so this will be 90 degree. Here also this is the tangent, this is the radius, this will be 90 degree. Now you can visualize that there are two triangles. Both are having these two angles as 90 degree. Can we prove them to be congruent? And somehow with the help of CPCT, that is corresponding parts of congruent triangles, maybe we can reach the required thing, that is PQ is equal to PR. Let us try it. Now here in these two triangles, let us first take these two triangles. In triangles PQO and PRO, what do we have in common, or what do we have the same measurement? We have angle PQO is equal to angle PRO, which is equal to 90 degree. Why? I just said that because radius is perpendicular to tangent at the point of contact. So clearly in both the triangles we have these two angles as 90 degree. Another thing which is same is that PO. PO is the common side between the two triangles. So it is equal. So PO is equal to PO because it is common. Anything else that you find that which is same or of equal measurement? Yes. OQ is equal to OR. Can you tell me why? Because they are radii of the same circle. So OQ is equal to OR, radii of same circle. So we have two triangles in which three parts are equal. One is 90-degree angle, this side which is common, and these two which are radii of the same circle. Can you tell me which congruency will be applied here? Of course, ASS is not an option. We know that it is not a congruence rule. So we can apply right angle hypotenuse side. Right angle hypotenuse side. So we can say that triangle PQO is congruent to triangle PRO by RHS rule. But what do we need to prove? We need to prove that PQ is equal to PR. Can we get it? Yes. First two terms here, first two letters here, we get PQ is equal to PR by CPCT, that is corresponding parts of congruent triangles are equal. Children, can you prove the same theorem without applying congruence rule? Is it possible? Let us try it. In triangle POQ. Now what kind of a triangle is this? This is a right angle triangle, as we have said that this angle has to be 90 degree because tangent is perpendicular to the radius at the point of contact. So in triangle POQ we can say that PQ is 90 degree. So which property can be applied here in this right angle triangle? The property is Pythagoras property. So Pythagoras property, when applied to this triangle, it gives us that hypotenuse square is equal to sum of squares of its sides, right? Now, so we can say that PO square minus QO square is equal to PQ square. Now, PO is common between both the triangles. Can we replace QO with OR? Why is it possible or why is it true? Because OQ and OR, they are radii of the same circle. So we can clearly write OR in place of OQ. Now PO square minus OR square. These two are sides of which triangle? They are sides of this triangle, triangle POR. So in triangle POR, again since it is a right angle triangle, PO square will be equal to OR square plus PR square, or we can say that PO square minus OR square will be equal to PR square. So this term can be replaced by PR square. So we get PR square is equal to PQ square, and square rooting both sides, I'll get PR is equal to PQ. So haven't we reached what we had to prove? That is PQ is equal to PR, that is tangent from the external point to the same circle, they are equal in length. Children, we have just proved that when two tangents are drawn from an external point, by proving these two triangles as congruent and with the help of CPCT, we have proved that PQ is equal to PR. That is the length of tangent from an external point are equal. Now, is there any other inference that we can draw from this? You can see that if these two triangles are congruent and corresponding parts of congruent triangles are equal, so we can say that angle OPQ is equal to angle OPR. They are corresponding parts. Angle OPQ is equal to angle OPR. So we can say that the center of the circle lies on the angle bisector of the angle between the two tangents. So this is another result that we have got from this theorem. So children, this was part 1 of chapter 10 circles. I hope you have understood it and you will practice more questions based on them.